everyone. Hope you had a weekend. Let me remind you that we have our first assignment due on Wednesday. Let's just think about what we were talking about. I want to go over sort of the scheme that we followed. We did it for the infinite square well, but this general scheme will apply for more or less all of the problems that we encounter. So let's think about it. So what we were working on was this infinite square well, and we were given some initial state, some solution to the full time-dependent Schrodinger equation at some time t that we call t equals 0. And what we found is that if we could write it as a sum of some coefficient Cn times these so-called stationary states. And these stationary states we got from the time-independent Schrodinger equation. So the full capital psi of x and t is the general solution to the full time-dependent Schrodinger equation. And then the little psi of n of x is a family of solutions to the time-independent Schrodinger equation. And we could also determine the energy of each of those so-called stationary states. And so the steps that we follow to do all of this was, number one, is we solve the time-independent Schrodinger equation to get these family of little psi n of x. And what we had to do is we had to use our boundary conditions and normalization to figure out, most importantly, the energy En of each of these states. And, the integration constants that we get from solving this time-independent equation. There's two of those because the time-independent Schrodinger equation has a d2 dx2. Okay, and then what we did is we said, well, any particular solution to the full time-dependent Schrodinger equation can be expanded in terms of these stationary states. And so here's a solution at t equals 0, and it's written as a sum of Cn times little psi n. Now, what we have to do is, given this function, this solution, psi x of 0, we have to find all the appropriate Cn's. And the way we found those Cn's was by solving this integral, where we took the conjugate of a stationary state, multiplied it by this function. And since this is expanded in terms of the stationary states, we were using the orthogonality property where psi star n times, say, psi of m is going to be 1 only when n is equal to m. Otherwise, those are going to vanish. That's what makes these integrals easy to do. It's this orthogonality property. Okay, and so then once we found all of these coefficients, we have all the stationary states. Remember this e to the minus I en t over h bar? That was the time-dependent part of our separation of variables that we did. It had a simple solution. It was just e to the minus I times some constant. It was our separation of variables constant. It turns out to be the energy times t over h bar. So once we have these three elements, we combine them all together in the sum, and that gives us the most general solution to the full time-dependent Schrodinger equation. So what I want to say is that this solution is constructed from like a Fourier-like expansion of stationary states. It's like when you write a Fourier series, you have something like an an times sine x, or let's say a1 times sine x plus a2 sine 2x plus a3 sine 3x, and so on. So what you have to do is you have to find all those a coefficients, and you do it in exactly the same way that we're finding them for our wave functions here. So in some sense, these Cn coefficients tell us how aligned our full solution is with a particular stationary state. Or if you don't like aligned, like what fraction of our full wave function comes from stationary state psi n. All right, so what I want to do is I want to be able to interpret the physical meaning of these CNs a little more clearly. And so that's what we're going to start with. And then we'll start, after we do that, we will go and tackle a new kind of problem. All right, so what I want to do is I want to return to this solution. It's the thing that I just reviewed. It's a sum of some coefficient Cn times our stationary state times the time-dependent part, like so. And what I want to do is I want to consider first psi n star multiplied by, oh, sorry, not psi n star, just psi star multiplied by psi dx. So this would be like our normalization requirement. This should have to be equal to 1. And so let's see what we get. All I'm going to do is take this thing and sublimate here. All right, so it'll be a bit of a mess, but it's manageable. So we'll start with n equals 1, and we'll have a C1 star, psi1 star, e to the minus I e1, t over h bar, and we just keep going. I'll write out a few of these terms, but these are infinite sums. I think what I'll do is I'll just go up to Cn psi n. Okay, I haven't been writing x, so e to the minus I e. Oh, okay, what have I've got something wrong here. What do I have wrong? Was that the sign, right? Yes. I am taking the conjugate, so there's no minus in front of the I times. So we'll get rid of that. The minus sign will come in this next part. And so I should be explicit that this sum keeps going. Okay, and then we have to multiply that by C1, psi1, E. Now I have the minus sign. E1, T over H bar, plus C2, psi2, E to the I E2, T over H bar, plus and so on, up to Cn, psi n, E to the minus I n, T over H bar, and it keeps going. Okay, and so then we multiply all this stuff out. I'll start just with the term 1 times term 1, 2 times 2, n times n, and so on. And then we'll deal with the cross terms after that. Okay, so the direct product is pretty straightforward because the exponentials are going to cancel. They have opposite sign. C1 star times C1 is just the absolute square of C1. And then we have psi1 star times psi1 is the absolute square. Okay, and we still have an integral, and and there's still going to be a whole bunch of terms to think about. Okay, and then we're going to have the direct product for n equals 2, and so on, up to n equals n. Cn squared, psi n squared, and so on. Okay, and now we'll start thinking about cross terms. Okay, so we'll do C1 star times the C2 term. So we're going to get a C1 star, C2, psi1 star, psi2. And then we have e to the, let's go minus I. So which one has a minus sign? I should have a minus sign here. Here's what I should have. I should have a minus sign here. So we'll get an E2. And then we have a plus E1, but I have a minus sign out here, so I'm going to write it as a minus E1. and then t over h bar. I'll write one more cross term. We'll do C1 star with Cn. So it's going to be psi 1 star psi n e to the minus I. It should be En minus E1 t over h bar. And, you know, there's an infinite more cross terms. But I think we've done enough to see what's going to happen here. So what I'm going to do is I'm just going to distribute the integral. Okay, so we'll do a little more writing. So this is going to be equal to C1 squared integral psi 1 squared dx. So first of all, what's this integral going to be equal to? 1. So if these are normalized stationary states, then the square of psi 1 squared is a probability density. What's the probability of finding the particle at some position? If we look over all space in our domain, then that probability has to be 1. All right, and then that's going to continue. So we'll get a C2 squared integral of psi 2 squared dx. But of course, that is 1 plus and so on, plus Cn squared psi n squared and dx. That's going to be another 1. And we get plus and so on. So those are the direct product terms. And so now we have cross products to deal with. So the first one is going to look like, let's see, C1 star, C2, and then this integral is over x, and so the exponential has nothing, it has no x dependence, so I could pull it outside. So it's e to the minus I e2 minus e1 t over h bar. And now the integral. So it's psi 1 star, psi 2 dx. All right. What's this integral going to be? 0. 0, because remember, we had this property that psi m star psi n dx was equal to delta mn. So this little expression is very important. It encapsulates the normalization requirement, where if n is equal to n, this has to be equal to 1, and the orthogonal requirement, where our stationary states, when you evaluate this integral, it evaluates to 0 if m is not equal to n. And this is the property that's going to make this expression look so clean, even though we started with something that was rather, well, let's say, intimidating. Okay, let's just do the second cross term that we wrote down. We have a C1, okay, we'll do plus and so on until we get to the C1 star, Cn, then we get e to the minus I, En minus E1, t over h bar. And I have to sneak in here the integral of psi 1 star psi n dx. That again is going to be 0. There's going to be a whole bunch more cross terms that I'm not going to write down. They're all vanish. And so we get this nice compact result where, you know, we started with this expression, which really is psi x of t squared dx. And the only thing that survives is C1 squared plus C2 squared plus and so on up to Cn squared. And then there's more after that. And if our wave function is normalized, that all has to be equal to 1. Okay, so these little coefficients that we found are required so that when their squares are all added, they have to be equal to 1. And so the normalization is encoded in these coefficients. All right. Let's do one more little extension, related extension of this. Let's calculate the expectation value of the energy. So remember, the way we calculate expectation values is we have the integral of the conjugate of our wave function and the wave function itself, like this. And what we have to do is, if I wanted the expectation value of, say, position, I would put my position operator here, x, and this would be the expectation value of position. If I wanted momentum, I would put my momentum operator here, and that would be the expectation value of momentum. If I had some operator q, I would stick it in here, and I would get the expectation value for whatever q represents. So we want energy, and our energy operator is the Hamiltonian. And so that was h hat. Really, h hat, this is just the time independent Schrodinger equation. Okay. All right. So fair enough. Let's just write out some terms. So it's the integral of C1 star psi 1. Okay, sorry. Let's do psi 1 star e to the I e1 t over h bar C2 star psi 2 star e to the I e2 t over h bar plus and so on cn star psi n star e to the plus I e n t over h bar. All of that has to multiply the unconjugated wave function, but we're going to have our operator acting on each of those. So C1 is just a constant. It's maybe complex, but it's still a constant. Then we get h hat acting on psi 1. And then we have e to the minus I e1 t over h bar plus C2 h hat acting on our second stationary state, e to the minus I e2 t over h bar plus and so on, plus Cn h hat psi n e to the minus I en t over h bar. And more, and there's more here as well. Okay, so I'm not going to write out all the direct products and all the cross products again. It's the same as what we just did. What I will highlight is that what was special about these stationary states is they all had a definite energy. Okay, and the reason they have a definite energy is because they're specifically the solutions to the Hamiltonian. They're the solutions to the time-independent Schrodinger equation. And so this was E1 psi 1. And this one, this one is E2 psi 2. Oh, crap. So, 2. All right. And then this one is En psi n. And now everything we did is exactly the same, except for we have this extra factor of the energy that comes along for the ride. So wherever we see a C1, it's going to be multiplying an E1. And if you go and write out all the direct product terms and all the cross product terms, what you're going to find is C1 squared E1 plus C2 squared E2 plus and so on plus Cn squared En plus more terms. And this is the expectation value of the energy. And we could write it more compactly in this way. So another way to interpret these CN coefficients is that they're telling us the probability that a measurement of the energy will find our system in a particular state. So the probability that a measurement of the energy will yield E2 is C2 squared, the absolute square. And same thing, the probability that we find our system in state N is Cn squared. Okay, so the other thing that's nice about this is, look, we started with some complicated time-dependent wave function. Nevertheless, when we write them in terms of our stationary states, we find that the expectation value of the energy is a constant. So whatever our initial state was at time t equals 0, it has some expectation value for the energy. At some time later, that expectation value has not changed. And so this is the manifestation of conservation of energy in our quantum system. So the expectation value of the energy is independent of time. That is, it is a constant of the system. And the other thing that I would highlight is that a measurement of the energy must yield one of E1, E2, E3 up to En and En plus 1 and so on. It has to give one of the stationary states. For example, when we solved the infinite square well, we found that there was only certain energies that are allowed. So if I'm going to measure the energy, I better get one of those allowed values. And then these coefficients tell us the probability of getting a particular result. So a measurement must yield one of the ENs, and the probability of getting En is given by this absolute square of that coefficient. All right, and so we've demonstrated this for the infinite square well, but these just general prescription applies to all of the quantum systems that we'll consider. And what we're going to do now is we're going to consider our second system. All right. So we are, I think this is section 2.3. And it's the harmonic oscillator. I won't write it down, but I will tell you why the harmonic oscillator is worth understanding. Just think classic, yeah. You must yield one of the En. Sorry, I'm not. You're this line?
Yeah.
A measurement must yield one. Oh, yeah. Yeah, who cares? Yeah, thank you. Yeah. Good. All right. So, harmonic oscillator, let's just think classically. Harmonic oscillator has a potential energy of 1/2 kx squared. And so x squared is obviously a parabola. And the reason that the harmonic oscillator is so important in classical physics and quantum mechanics is because often we're interested in the low energy behavior of a system. So if you just think about any potential, I don't really care what the shape is, v of x, here's x, it can be some complicated thing, then if I'm interested in the low energy dynamics, maybe my system has an energy here, then the potential is in this region, maybe it's not exactly quadratic, but I could certainly approximate it as quadratic. And so as long as I'm interested only in a narrow range of x values close to this minimum, this potential could be arbitrarily complicated, but over here, it looks like a goddamn quadratic. And so the system's going to behave like a harmonic oscillator. And so harmonic oscillator shows up over and over and over again. Okay, so we know the potential energy of a harmonic oscillator is V is 1/2 kx squared. Okay, now if you think about the force, MA, I could write as mx double dot is equal to minus kx if I had, say, a mass on a spring. And so here's my spring and here's my mass. Okay, well, I could rewrite this as x double dot is equal to minus k over m x, and it's customary to write this as minus omega squared x, where omega squared is equal to k over m. The reason you write it like this is because, everybody knows what's going to happen. If I stretch this spring and release the mass, it'll oscillate back and forth harmonically like sine omega t. And that omega, the frequency of those oscillations, is given by the square root of k over m. Okay, so if I wanted to, I could replace the k in this potential as m omega squared, and that's typically what is done in a quantum mechanics treatment of the harmonic oscillator. Okay, so there's our potential. And what we're going to do is we're going to sub into the time-independent Schrodinger equation. Notice we're not even going to bother working with the time-dependent Schrodinger equation. All we're going to do is solve the time-independent one, find our stationary states, and then we could build solutions to the time-dependent Schrodinger equation without ever writing down that differential equation. Okay, so when we do that, h bar squared over 2m d2 psi dx2 plus v of x. Okay, v of x is 1/2 m omega squared x squared, and then we have to multiply by our wave function. That has to be equal to e. E was originally our constant when we did separation of variables, but we now know it's the energy times psi. Okay, and so this is our v of x. All right, good. So what we really would like to do is we'd want to solve for the stationary states psi of x and find the energy of each of those states. Okay, now we're going to do this in kind of a tricky way. And so it'll be a bit of a long, kind of drawn out calculation, but it's pretty neat actually when you sit back and appreciate it. Okay, so let's get a start on this. Recall that our momentum operator is minus I h bar d by dx. So if we act on a wave function with this operator, it returns the momentum times that wave function again. Okay, so what I'm going to do is I'm going to rewrite this time-independent Schrodinger equation in terms of this operator. So if I act with this operator twice, I'll get a h bar squared and two derivatives of x, and you can see it right there. It's the first term in the time-dependent Schrodinger equation. So time-independent Schrodinger equation. Okay, so we can express as, all right. So the p hat squared gives us our minus h bar squared. I still need to put in the 2m. I mean, you can see p squared over 2m. That's a way of writing the kinetic energy, right? So there's our kinetic energy term. Then we have our potential energy term. All of that multiplies the stationary state we're trying to find, and then that has to be equal to E times psi. All right. Or if we want to write this a little more nicely, I'm going to pull out a 1 over 2m. And so we end up with a p hat squared plus, let's see, I pulled out the 1/2. I pulled out a m in the denominator, so this becomes an m squared. So I have m, omega, and x, all of those are squared. And then we have psi is equal to E psi. So if you look at the structure of this is our Hamiltonian, right? So this is our h hat. The structure is something squared plus something squared. Now, if you had that not in terms of operators, but just in terms of like numbers, you could factor that. So we can factor something like, so suppose we had u squared plus v squared. I could write that if I wanted to as I times u plus v minus I times u plus v. If you multiply this out, well, what are you going to get? You're going to get u squared times minus I squared. But I squared is minus 1, so you just get u squared. Then you get v times v is v squared. And just to make a point, I'm going to write this as plus IUV. And then I'm going to write it as minus I. And then I'm going to preserve the order of this. It's V times U. Now, of course, for regular numbers, this is going to cancel, okay? And so this cancels for ordinary numbers. Now, what I want you to keep in mind is we're going to do something like that to our Hamiltonian. But the U and the V are going to be operators. This thing is going to be like a derivative with respect to x. And it's not obvious that it's going to cancel if I have a derivative with respect to x times a function of x. That's different than a function of x times a derivative with respect to x. So let's just keep that in the back of our minds as we work through this. So we're going to try something similar. Whoops. Similar with, okay, the part that I want to work on is p hat squared plus m omega x squared. So, however, we're going to keep in mind that this p hat is proportional to a derivative with respect to x, and it is an operator. In general, it is not the case that something like p hat x is equal to x p hat. Okay. All right. Nevertheless, let's push forward. Now, the way we're going to do it is admittedly a little bit abstract, but let's just see what happens. So to do this, we're going to define a new operator. And so this operator, we're going to call it a hat. And in fact, there's going to be two of them. There's going to be a plus and a minus one. And so the way they're defined is there's going to be some prefactor that's just written there for convenience. We'll see why it's convenient in just a little bit. But here's like the factoring part of it. Remember, when we factored u squared plus v squared, we ended up with an iu plus v. So we're going to have the same sort of structure here. There's my iu-like term. It's going to be I times p hat. And in fact, I could put a minus or a plus here. When I did this factoring above, I could have had, I don't know, like I could reverse the plus and the minus. It wouldn't make any difference. All right. And then we'll have a plus. The other one, this is like the v. It's just m omega x. So this is the exact factoring that we used for our numerical example. I just added some prefactors out front. Okay. So what I want to think about then is the product of these two operators. So then a minus times a plus, what's that going to give us? Okay, so the prefactor is going to be squared, so we get a 1 over 2m h bar omega. And then I'll just write it out. So we're going to put, let's see, which one are we going to put first? Notice it's a little weird, right? The plus operator is the one that has the minus sign in front of the IP hat. We'll see why we did that again in a moment. And then the minus one has the plus sign. So we'll start with the I p hat plus m omega x, and then we have minus I p hat plus m omega x. And all we're going to do is expand this product and see what happens. Okay, 1 over 2m h bar omega. Well, I times minus I is just plus 1. So we get our p hat squared. That's familiar, so that looks good. Let's do this one next. M omega x times m omega x is obviously just m omega x squared. Oh, that's good. That's also familiar. But now we have our cross terms. And let's see, we're going to get a I m omega p hat times x. So we'll have a, how do I want to do it? I m omega, and then we'll have a minus p hat x. Okay, so if I multiply through, the minus signs will cancel. I'll get I m omega p hat x. I m omega p hat x. So that's that times that. So then we have this times this is going to be minus I m omega, and then it's x p hat. So x p hat is what we have. Okay, good. So you can see what the problem is going to be here. This is x times the derivative of x. This is a derivative of x acting on x. And so it's actually going to kill this. And so these things don't cancel. And so that's the issue. So x p hat minus p hat x is called, it has a name. It's called the commutator. Commutator of x and p hat. Not only does it have a name, it has its own little notation. It also has a special notation. And that notation is square bracket x p hat square bracket with a comma between them. That is just defined to be x p hat minus p hat x. And so the order matters. Like p hat x is not the same thing. It would reverse these terms. It would pick up a negative sign. Okay. So we would like to know if there's a way that we could evaluate this commutator and write it in a simplified form. So to evaluate commutator relations, the strategy is the following. And this is a general strategy. There are lots of commutator relations, not just x and p hat. And so this strategy applies to all of them. Is we act on a dummy function, f of x, that helps us to keep track of how the operator acts. In the end, we will just drop the f of x dummy function. We'll show you an example so you can see exactly what I'm talking about. So here's the commutator of x and p hat. And what I'm going to do is I'm going to make up some function. I don't even have to have a form for this function. It's just some function of x. And then we just write out the commutator. It's x p hat, but then it's going to multiply f of x. So I'm going to have f of x, and then we have minus p hat x, and that also has to multiply our f of x. So in fact, what I want to do is I want to highlight the fact that now this p hat is operating on two functions of x. And we have to use product rule to do that. And so that's the reason why we act on a dummy function. It's just to see the fact that product rule is going to be at play here. Okay, so let's see, p hat is minus I h bar. And then we have x, and then d by dx acting on f of x. Okay, so this minus I h bar times the derivative, that's the p hat. Okay, and then we have minus. Well, what we have a d by dx, but this time this derivative acting on, like I said, a product of functions of x. So we have to do product rule, and so we might as well do that. Minus I h bar x df dx minus, okay, so we take the derivative of x, and we're just going to get an f. And then we have plus x times the derivative of f. Okay, but look, we have a minus sign out front here. So this x df dx is going to cancel with this x df dx. And if we didn't create our dummy function, it would be very hard to keep track of that cancellation. That's the utility of making up this f of x. Okay, so we do that cancellation, and what are we left with? minus signs that cancel, we get IH bar times F. And now is the time where we can say, look, dummy function, you've served your purpose, thank you very much. Now we're going to drop it. And we're just left with, therefore, after dropping, dropping f of x, we're left with the commutator of x and p hat is just equal to I h bar. And so what we're going to do is we're going to go way back here and we're going to say this thing is the commutator of x and p hat. I'm going to call this whole expression star. And now we're going to go back to star. And here we're going to put whatever it was, like IH bar. Okay. So yeah, it was IH bar. So now we return to star and use xp hat. Commutator relation is IH bar. Okay, and so remember what we were trying to do was to evaluate this product of these A operators, A minus and A plus, which represent the factoring of our Hamiltonian. Okay, so we had a prefactor, 1 over 2m h bar omega. Then we had our direct terms, p squared, and we had m omega x squared. And now we're going to put in our commutator results. We had an I m omega times the commutator, which we now know is IH bar. Okay, so this is starting to look a little bit better. So what can we do? The I times minus I is going to be a +1. When I bring in this prefactor, m omega h bar, m omega h bar, all going to cancel. So we're going to get a 1/2 from this term, a +1/2, as a matter of fact. And so this is equal to 1 over h bar omega, 1 over 2m. And then we had p squared plus m omega x squared. Okay, so that's the first two terms. I've just written it down exactly as it was. But now I'm going to separate out this one. And I'm going to do all that cancellation. And we just get a +1/2. So this factoring trick didn't work exactly the way it did for numbers, but it worked out pretty nicely. We just picked up a 1/2 here. Okay, but otherwise, the factoring worked quite nice. As a matter of fact, all of this stuff here is exactly our Hamiltonian. If you look back, that's exactly what we had. So if we solve for h, solve for h hat, we're going to get that h hat is equal to. Well, let's see. The first thing I'll do is I'll subtract off the 1/2, and then I'll multiply by h bar omega. So it is h bar omega, and then it's a hat minus a hat plus minus 1/2. And so what we've managed to do is we've managed to rewrite our Hamiltonian in terms of these new operators, where these operators are like the factoring trick that we employed. It's going to turn out to be very convenient. Okay, so we have re-expressed our Hamiltonian. And when I say Hamiltonian, you can think time-independent Schrodinger equation at h in terms of our new a hat plus minus operators. Okay, so therefore, one way to write the time-independent Schrodinger equation is h hat psi is equal to h bar omega a minus a plus at minus 1/2 times psi is equal to e psi. Okay, so there it is. That's our time-independent Schrodinger equation. I'm going to call this equation A. Now, we made an arbitrary decision to work out the product A minus and then A plus. We didn't have to do that. I could have, when I did my factorization, I could have said, okay, I've got my two factors. Let's do A plus times A minus. And you can do that. And if you do, what you'll find is using the same line of reasoning, we can also express A plus times A minus. So I reverse the order of this product. And we've already seen that reversing the order of how an operator acts is not equivalent. I don't expect A plus times A minus to be equal to A minus times A plus. Okay, so if you do this, what you will find is that this is equal to our Hamiltonian divided by h bar omega minus 1/2. And if you compare to what we had before, we had plus 1/2 last time. And you can understand why the result is just a change in sign, because our commutator between x and p hat gave some results. If I did the commutator between p hat and x, I just get the negative of that result. And so that's why it's just a negative sign in the commutator term. Okay, so therefore, there's another way for us to write down our time-independent Schrodinger equation, and it is h bar omega a plus times a minus, and then it's plus 1/2 times our stationary state is E times the stationary state. And so this is a second version of our time-independent Schrodinger equation. Of course, the right-hand sides are identical, so the left-hand sides have to be equivalent. So in fact, what I'm going to do is I'm going to take the difference between A and B. So if I was to look at equation A minus equation B, it's going to be equal to, well, h bar omega. And so equation A was, equation A was A minus A plus, and then minus 1/2. And then B, I'm going to subtract B, and so that's going to be A plus A minus is plus 1/2. And then, so that's the left-hand side. The right-hand side is E psi minus E psi, which is just 0. 0. Okay. Well, let's see, what does that mean then? I don't care about the h bar omega. I divide by h bar omega, 0 divided by whatever is 0. So I only care about what's in the square brackets here. A minus A plus minus A plus A minus. So therefore, a minus, a plus, minus, a plus, a minus. Well, and then what else am I going to have? I'm going to have a minus 1/2, minus 1/2. So I'm going to get a minus 1 is equal to 0. Or I could write all of this stuff is equal to plus 1. So this is equal to 1. But what is this thing? What did we just define some new stuff? It's a commutator. That's exactly what it is. So this is the commutator of a minus and a plus. And so therefore, we have another commutator relation. This one's equal to 1. Now you could say, well, why did you arbitrarily decide to do equation A minus B? I could have done B minus A. And you're right, I could have done that. What would I get if I do that? What do you think I would get? We're going to get a negative 1. And what's going to be different here? We're going to switch the, yeah, exactly. So it's exactly the same thing we saw with the plus minus 1/2. If I switch the order of these, all I do is pick up a minus sign, right? If I switch the order, I just put in a minus here and a plus here, and then I'll get a minus over here. Okay, so by the same reasoning, if I was to do equation B minus A, we will find that this commutator is equal to minus. Okay, good. And so we're going to use some of these properties as we try to solve the Schrodinger equation, the time-independent Schrodinger equation, to find these stationary states. And again, it's going to be a little abstract, but let's just keep pushing ahead. And so here's my first abstract claim. If we had some psi, some stationary state that is a solution to our time-independent Schrodinger equation. So let's suppose psi is a solution to the time-independent Schrodinger equation. H hat psi is equal to E psi. Then I claim that A plus times psi, acting on psi, it's an operator, and also a minus acting on psi, those are also solutions to the time-independent Schrodinger equation, are also solutions. Okay, so here's the proof. And the proof will use these commutator relations that we just wrote down. All right. Okay, so let's take this funny looking thing. So this is the Hamiltonian acting on this. Think of everything in the brackets as some new state. It's some new state that's generated by acting on a known stationary state with this operator, okay? And we'll come up with an interpretation of what that operator is doing, but that will have to wait just a little bit. Okay, so all I'm going to do is write down our Hamiltonian, the factored version of it. And that was h bar omega. One version of it was a plus, a minus, plus 1/2. Okay, so that's our Hamiltonian. And then we're gonna have our new state that's generated by acting on the known state times this operator A plus. Okay, so now we're just going to do a little bit of algebra. The only thing you have to be worried about is that I cannot arbitrarily change the order of the operators. The operators can pass through constants like 1/2 and h bar and omega and stuff like that, but I cannot take this A plus and I can't move it past the A minus, for example. So that's the only thing that we have to be cautious about. Okay, so my first order of business is going to be to distribute the A plus. And I can't pass those operators, so I'm just going to stick it on the end here. Okay, so we have h bar omega, A plus, A minus, A plus. So we got this little daisy chain of A operators, plus 1/2 A plus. So, okay. So now what I'm going to do is I'm going to notice that I have now A plus on the left here, and I also have an A plus here. So what I can do is I can take this A plus, and I'll put it over, oh, whoopsies, I wanted a different color. I'm going to take that A plus and put it over there, and this one I'm going to take over here. So then when I multiply it back through, I get 1 there in the right spot, and I get 1 there. Okay, so that's fair enough. Okay, so this is equal to A plus h bar omega. And then what's left over? A minus A plus 1/2 times psi. Okay, good. Now, the next order of business is to use one of our commutator relations. We're going to use the one where A minus and the commutator of A minus and A plus is +1. Okay, so let me just remind you, the way you write these commutator relations down is the left times the right minus the right times the left. So it's the left times the right minus the right times the left, and that has to equal to +1 in this case. I have a A minus A plus in here, and what I'd like to do is I'd like to rewrite that in terms of A plus and A minus. So if I solve for A minus A plus, it's going to be 1 plus A plus A minus. Okay, and so what we're going to do is we're going to take this thing and we're going to stick it in there. Okay, so what we're working on here is the Hamiltonian acting on A plus acting on psi. And we have A plus h bar omega. Okay, and so now I'm going to write this as A plus A minus +1. And then we still have our +1/2. Okay, so it's going to be A plus A minus. I'm going to write the 1/2 first, and then I'm going to write the +1, and all of that's acting on psi. All right, so let's see. A plus h bar omega, A plus A minus +1/2 times psi. Okay, so I'm separating out the +1. So when I take out the +1, it has to have the A plus h bar omega, and it has to have the psi. So we end up with a plus A plus h bar omega psi. All right. Now, I want to extend that a bit further. If you look back in our notes, this is one version of the Hamiltonian, the time-independent Schrodinger equation. This is H hat acting on psi, which we know is E times psi. Okay, so what we have then is A plus E times psi. I'm going to write that as E A plus times psi. I can take constants. I can move constants around my operators. I can't move operators around each other. Okay, and I still have this thing. I'm going to write this as h bar omega, A plus times psi. So we get a plus h bar omega, A plus times psi. Okay, so we're very close to where we want to be. H hat acting on A plus psi is equal to, we have a common factor here, A plus psi. So this is equal to E plus H bar omega, A plus times psi. Okay, this is the result that we wanted to get. And so let's just reflect on trying to interpret what it means. We assumed that we had some function psi, which was a solution to the time-independent Schrodinger equation. It had an energy E. Okay, so psi is a solution to H hat psi with energy E. And what we've just worked out is that A plus acting on psi is a solution to H hat, to our time-independent Schrodinger equation. And it has an energy E plus H bar omega. And so what we've been able to do is by taking one known solution, we didn't even have to write down what that solution was. We just presumed that there is a solution with some energy. Then we've figured out that we can generate another solution just by acting on the known solution with our A plus operator, and we get a state with energy E plus H bar omega. It's kind of amazing because we haven't even written down a functional form for any solution, but suddenly we're able to say that we can find new states with energies that are just E plus some constant, H bar omega. I could do that again. I could say, well, if this is some solution, I can act on this with A plus again, and I'll generate a new state. It'll have energy E plus 2 H bar omega. And then I act again. And I'll get E plus 3 H bar omega. And I do that over and over and over and over again. And what this is getting to is that if I am able to actually write down a functional form for one solution, I'll be able to generate an infinite number of other solutions. And that's in fact exactly what we're going to do. Okay. Now, I've said this twice already, but what we could have done is we said, well, why did you pick A plus? What if I put an A minus here and I used the version of the Hamiltonian that went A minus A plus minus 1/2? What would happen if I did that? You could probably tell me, what do you think? It is going to be a solution to the Hamiltonian, the Schrodinger equation. What's the energy going to be? There's no wrong guesses. What do you think this is going to be? E minus h bar omega. And so this is why we've labeled the A plus operator with the plus sign, because it generates states of higher energy. The operator with the minus sign will generate states of lower energy. Okay, so using similar reasoning, we would find that a minus hat acting on psi is also a solution to our time independent Schrodinger equation with an energy E minus h bar omega. It generates a state of lower energy. So once I find one state, I can generate an infinite number of states with higher energy, and I can generate states with lower energy as well. Okay, how are we doing time-wise? Oh, we've only got a few minutes left. So if we can find one stationary state, we can generate an infinite set of other states by acting with the so-called, so the A plus operator is called a raising operator because it generates a state of higher energy. So a raising operator, A plus, and a lowering operator, A minus. The collection of these two operators are sometimes called ladder operators. And there's a picture in your book of a cat going up a ladder. And so I can go up the ladder to higher energy states with the raising operator, and I can go down the ladder to lower energy states with the lowering operator, A minus. Okay, so next time, what we're going to do is we're going to actually generate one stationary state. Once we've generated that one state, we'll be able to generate all of the other ones. The beautiful thing is that we already know how the energy spacing will go. The spacing is just going to be equally spaced states. The spacing between state n and n plus 1 will just be h bar omega. So we're going to generate one state, we're going to find its energy, and then suddenly the whole problem is solved. Okay, so that's the plan. If you want to come to class prepared on Wednesday, I'll tell you the first thing we're going to do is we're going to look at problem 2.2. And 2.2 is going to be essential for us to create that first state. As a matter of fact, the first state that we will generate is the ground state, the lowest energy state. And then from there, we will act with A plus to generate higher and higher and higher energy states. All right, good. So that's where I want to stop. And it is the correct time to stop as well. So that's good news. Thank you very much.
Are we going to touch on like matrix representation of operators and what's on?